Hey AP, in this video we are going to look at ice tables. So in yesterday's video we looked at equilibrium and equilibrium expressions, and in all of our calculations we were working with concentrations that were at equilibrium. But most of the time in real life, we are not going to get concentrations that are at equilibrium. We're going to get initial concentrations, and then we're going to mix things together or disrupt an equilibrium, and then we want to see, well, what is going to happen when our system reestablishes equilibrium. So that's what we're going to look at today. So when a problem gives you initial concentrations and not equilibrium concentrations, we use something called an ICE chart. And ICE stands for I for initial, C for change, and then E for equilibrium. So just like in anything else, there's a stoichiometric change in the equilibrium reactions, just like regular reactions. And the amount of product formed is dependent upon the mole ratio of the reactant. And that's what we've been looking at, right? If we have, a 2 in our reactants and a 1 in each of our products, right, it's going to have a 2 to 1 to 1 ratio. So that's nothing new. So let's look at what kind of questions we can get asked, and then how are we going to set this up based off of our new information. So before we talked about Kc and Kp, which are both equilibrium constant or equilibrium constants, which is depending upon if we have Kc, which is our concentration, meaning things need to be in molarity, and Kp, which is pressure when we're looking at things in their partial pressures. So in our first example, we have 4 moles of HI, which is hydroiodic acid, is placed in an evacuated 5-liter flask and then heated to 800 Kelvin. The system is allowed to reach equilibrium. What will be the equilibrium concentration of each species? So we can see our balanced chemical equation. We have HI in equilibrium with I2 and H2. We're told our K value, and we are told the temperature that it's at. So we're going to let X represent the change in concentration of the hydrogen gas and our iodine gas and our HI. Before we can start by writing things in, notice that we need initial concentrations, and we were told moles and volume. Remember that molarity is moles per volume. So if we were given 4 moles to start in a 5-liter container, that is 0.8 molarity or moles per liter for my initial concentration. So my initial concentration, the only thing that I know about is my HI. So I'm just going to write my ice closer here. So my initial concentration is 0.8 molar. Before I start, I don't have any of either of my 2 products. So both of these are 0 because I don't have any. I haven't done the reaction yet. Because I have reactant and no product, the only way that my reaction is going to proceed is to the right. So that means that this amount, my reactants, is going to decrease by some amount, and my products are also going to increase by some amount. And this is where that stoichiometric change comes into play. We have to carry down our coefficients to figure out, well, how much change we're going to have. So this is decreasing by 2x because of the 2 here. This is increasing by 1x and 1x. And we don't have to write the 1s in. So that means that at equilibrium, I have 0.8 minus 2x is my concentration for HI. For I2, 0 plus x, which is just x, 0 plus x, which is just x. Now, the cool thing is that we know an equilibrium expression. We know the equilibrium expression for this reactance is products over reactants raised their coefficients. So that is the concentration of H2 by I2 over HI squared, again, because of that 2. And we know the K is given to us here. We know that this equals 0.016. So that means by plugging in each of these variable expressions in for our concentrations, we could solve for X, and then we could figure out, well, what are their equilibrium concentrations? Well, let's go ahead and do that here in this practice problem. I have 0.6 moles of HCl placed in an empty 2-liter flask. System is allowed to establish equilibrium. What will the equilibrium concentration of each species, that just means each compound, in the flask be? Given my balanced equation, I know that I have initial concentrations, right? I'm initially doing this, so that means I need to create my ice chart. Remember, I want concentration, which is moles per liter. I'm given 0.6 moles. I have 2 liters, which means I have 0.3 molar to start. So my HCl is 0.3 molar. I don't have either hydrogen or chlorine, so those are both 0. The only way that it can proceed is by shifting to the right. So that means this is going to decrease by 2x, and both of these are going to increase by some amount, x. It means at equilibrium, my HCl concentration will be 0.3 minus 2x. I'll have x and x. Just like before I said, well, if we know K, we can also calculate our Keq expression since we know our reaction. So for this reaction, Keq is equal to my products, H2, Cl2, over their reactants, HCl, raised to their coefficient, which is the 2. Keq, we know, is equal to 0.5. And then I can plug in for each of my values here at equilibrium. So H2 is x, Cl2 is x, HCl is 0.3 minus 2x, that quantity squared. Now we can rewrite the top, x times x is x squared over 0.3 minus 2x squared. And when I have a square on the top and a square on the bottom, I could also write this as x over 0.3 minus 2x squared. Okay, so what that does is that means I can take the square root of both sides and get rid of my square there. So that means I don't have to do a quadratic formula, which is lovely. So I'm going to take the square root of both sides. So my square root of 0.5 is 0.707. And that is equal to x over 0.3 minus 2x. Okay. From here, I need to bring this quantity up. So I'm just going to do that over here. I have 0.3 minus 2x, right? This is all just math from here on out. 0.707 equals x. I need to distribute through. So 0.3 times 0.707, 0.212 minus 1.414x equals x. I'm going to add my x's to both sides. 1 equals 2.414x. And divide 2121 divided by 2.4141. So 0.0879 equals x. So this, you can still see it, this part gets substituted in for everything up here. So 0.3 minus 2 times 0.0879. This x is 0.0879, and this one is 0.0879. So I like to rewrite things over on the side. So my concentration of H2, I2, HCl, and we're dealing with 3 sig figs. This is a constant, so I'm okay with what I've got. 79 molar, and then 0.3 minus 2 times 0.0879, 2142 or 1242 molar, which really 3 sig figs, we get rid of this 2, like so. So those are our equilibrium concentrations of our reaction after it's reached equilibrium when I start with 0.3 molar of my hydrochloric acid gas. The other thing that we need to be aware of is that when we're doing these calculations and we're setting up our ice chart, if we have a weak acids don't fully dissociate. So they don't fully break apart. That's what makes them weak. So their equilibrium concentration is considered equal to their initial concentrations. So if HCl, we know HCl is a strong acid. However, if it had been a weak acid, that means that the change in its concentration is considered negligible. So it would be 0.3 molar at the end, just like how it was at the beginning. And this is nice when you have one of these calculations because you have one less variable that you have to solve for. Usually it's a thing that's squared, and it makes solving your equation easier because the change is just so insignificant. You used to have to do a test to prove that its change was insignificant, but at this point, AP says, well, weak acids are unable to fully dissociate, so we're going to assume that equilibrium concentration is equal to initial because in the grand scheme of things, especially with sig figs, it really doesn't change at all. So we'll just be aware of that if we have any weak acids in our practice problems tomorrow.